In the last class we had motivated neural networks by talking about VC dimension. VC dimension was a measure of the power of a model. So we had talked of neural networks as giving you the power to create cascades of linear units, basically linearly separable units or linear separating units, and that was allowing you some amount of arbitrary non-linearly separable data to be separated. And we had shown you the prototypical case of the solved problem XOR where 1 XOR 0 is 1, 0 XOR 1 is 1, the rest 0 XOR 0 and 1 XOR 0, 1 XOR 1 are both 0, and for unfortunately you don't have it linearly separable. So you would expect some kind of some surface like this, and I showed you several examples. Similar examples as kind of nearly spirally separable data. That will be also part of your lab today. Lab assignment 3 will have some data like this, right? So you'll have to be able to train a neural network that achieves separability. XOR will also be a part of the data set. So how do you train such neural networks given that they have some good capacity to separate data? So we talk about backpropagation algorithms, flow graphs, and then move on to networks which have prior knowledge or common sense knowledge embedded into their architecture. So just recap this XOR network. So we had exactly one hidden layer. This was the input layer. This was the output layer. Can you have fewer than one hidden layers? What was your experience? So that playground thing, right? Yeah. So playground and tensorflow.org, we tried it out. So let's say I pick a data set, a classification data set, which looks like XOR, and if I try and achieve its separation using 0 hidden layers, you'll find that the training loss is stuck at 0.5 and so 0.49, which is 0.5, and test loss is stuck at 0.5. So if the data is not linearly separable, 0 hidden layers is not going to serve any purpose because it's basically logistic regression, right? So that was example of XOR. So you need at least one hidden layer, okay, and you can also justify this using VC dimension. How would you do that? So the VC dimension of a linear separator in R2 is 3, and we have 4 points here, right? So this is another justification. Fine. So with this now, we move on to how do you train such a network. I fix the architecture, and my architecture may be inspired by discussion on VC dimension. There could be some other inspiration for the architecture, but whatever be the architecture, how do I train it? my inputs xi's will be situated here. My outputs are here. For my training examples, which are xi, x1, y1, x2, y2, in general xi, yi, I observe the hidden layer, sorry, the input layer, I observe the output layer, right. So I could feed and kind of measure, calibrate, correct based on yi's, xi's. What I can't observe are, I can't observe what the activations at the hidden layers are, right. So while training, activations at input and output layer are visible. Like logistic regression, we had those activations visible and we trained the weights. The weights are all sitting here. These are the weights. The weights are on the edges. So I was training the weights in logistic regression, making these two observations, but unfortunately, with the additional power that I brought in, the activations at the hidden layers cannot be observed while training. So these activations are actually hidden even during training. Okay, so this is what you have to keep in mind while training the neural network. We have the inputs, the outputs, number of classes, and you design the hidden layer. Typically you design using one or more hidden layers, and typically the number of hidden units are of the same order. Okay, so this is I would say a general rule. Number of hidden units in each layer is a constant factor of the dimension of x. They are of the same order. You won't have x in hundreds and then hidden the number of hidden units in a layer in the order of say tens of thousands. You won't do that. And I'll kind of explain using some more some more motivation why this would be done. But the issue is that these are not observed. Okay, so we need to address this issue. Okay, so for most illustration we will use this smooth sigmoid function. We have spent a lot of time on the sigmoid. It just makes our life easy in terms of derivatives, etc. Even in the last quiz I kind of asked one question on what is the derivative of sigmoid. So it's something you keep brushing up all the time. And we have now learned how to train a single node logistic regression network. Right? Logistic regression is basically a neural network with no hidden layers when you have the sigmoid activation. You could also use the non-smooth step function or something else, RLU, talked of tan h and so on, but we will stick to sigmoid for the time being. Now also recap the gradient descent algorithm. So when there is no hidden layer and the activation unit is sigmoid, then we were able to employ the gradient descent algorithm. Basically, it just boils down to a logistic regression problem and gradient descent. And the idea of gradient descent is using the negative of the gradient, because the negative of the gradient gives you the direction of maximum rate of decrease of the function. Okay, and you have done this until some stopping criterion is satisfied. Graphically, what's happening? So, level curves. You all know level curves. So, these are, let's say, these are some level curves of function of some function f of x1 comma x2. So, this is x1, this is x2, and each level curve corresponds to some constant value, right, some constant value of the function. And gradients, what are those? The gradients will be perpendicular to the level curves at the respective points. So, here we have shown level curves only for some select values, some select level curves, right. So, we have shown select level curve for a function, and that too at select points. So, there are some selected points, not at all points. So, let us take this point here. Okay, so, at this point on the level curve, this is the direction of the gradient. At this point on the level curve, this is the direction of the gradient. And as you can see, the gradient is always perpendicular to the level curve. So, and take this point. Okay, so gradient is perpendicular to the level curve at that point, and as you can see, it points in decreasing value of the function. In fact, the fastest rate of decrease, the direction of fastest decrease. Oh, so a gradient, negative of gradient. This is a negative of gradient, and in direction of fastest decrease if you want. But fastest is in a specific sense of some Euclidean norm. Okay, and I mean, interestingly, these curves are for a quadratic function. As you can see, these look like ellipses, right? So, you can guess the nature of the function. Now, an interesting point here is smaller gaps between successive level curves correspond to shrinking rate of change of the function. Sorry, not increasing rate. I'm sorry for this. Increasing rate of the function. A smaller, when the function starts decreasing very fast, then what would you expect? The gaps to be small, right? So, here the rate, wherever the gap is small, here the gaps are becoming big, right? When the gaps are becoming big, then the rate is actually decreasing. Smaller gap, faster rate. Bigger gaps, smaller rate. Yeah, I mean, his question is, have we ensured that the C's are changing at the same unit? So, yes. Assuming C's are spaced out uniformly. Okay. So, diminishing gap between level curves, that is exactly what I have said. Faster change. Okay. So, now you can, I mean, this is something important to note, because when the gaps become very small, you might also accept some instability. Okay. So, that might come up later, but for the time being, this is a picture. So, now this is all fine when you have a nice convex function, but in reality, what you often have is something like this. The level curves would look something like this. See, what we showed was a quadratic function. For neural networks. So these level curves basically, or call them sub-level sets, the area inside. Now that turns out to be non-convex. I mean, this shape doesn't look like convex, right? Though that looks convex. So each of those looks convex. This is non-convex. In fact, highly non-convex. Now it may happen that you are going maybe the minimum, maybe there is a better minimum here, right? But I am stuck here and I will be basically descending here, whereas I should have been going here. Let us say the value here is minus 100 and here I am stuck at minus 10. So these different regions, escaping out of those regions will become important. Keep this in mind. So we are trying to do two things: illustrate what gradient descent does and where now we might hit the wall, or we might not be very effective in the case of neural networks. So you may do gradient descent here, but you may have to guard yourselves against these local minima. Okay, so when there is no hidden layer and sigma is sigmoid, then you have this. But when we have hidden layers, objective is non-convex. And what objective are we talking about? Okay, so keep this in mind. But we have a more serious issue when it comes to using hidden layers. Problem is non-convex. I mean, by non-convex I mean shapes become like that. But the bigger issue is that the hidden layers I don't even observe. I mean, in some sense they are related, because I am dealing with a very large unknown set of hidden layers. The problem becomes more difficult to tackle, and that is why it is not convex. They are actually related. So this also poses some algorithmic challenge. The algorithmic challenge is I need to impute or guess the values of the hidden layers. Okay, so the algorithmic challenge actually missing, instead of missing I will say unknown values. We need to handle unknown values of hidden layers, unknown activations. Okay, so the 2 points are related, non-convexity and this. So what you do, we will try and first address this issue. There is not much we can do about the second issue. I mean, few things we can do, but algorithmically is something we can do. So algorithmically what you do is backpropagation. Backpropagation, as I will very soon point out, is nothing but some kind of chain rule application and memoization. Have you done memoization so far? Where did you come across memoization? Dynamic programming. So you basically do bookkeeping, right, of intermediate computations. So algorithmically what you do is backpropagation. This is illustrated here. So let's say I have f x y z, which is written in terms of gf, gq and so on. What these gf and gq mean are basically activation functions. So think of this whole thing as f, there is f sitting here, but f is gf, which is now computed in terms of another activation at here gq. So gf requires gq. Now if the inputs are x, y, z, so x, y and z, these are the inputs, right? And if I want the gradient of f, I want the gradient of f with respect to these weights wx, wy, w, so these are the weights, and weights you see here color coded, these are the weights. If I want the gradient of f with respect to those weights, I need to be able to do something with respect to the hidden computation of gq, right, which requires u gf. G is the activation function sitting here. So think of gf as activation function sitting here, gq as activation function sitting here. So if I want this gradient of f with respect to these weights, what will I have to do? These weights are deeply into gq. So what do you know of? You heard of chain rule, right? So in this general setting, if I want df dou f with respect to dou wx, right, then what would I write this as? If you want instead of f you write it as gf, that's also fine because f is characterized by this activation function gf. So let's say partial derivative of gf with respect to what? gq, and the into partial derivative of gq with respect to wx. In the case of z, I may not need gq at all. The dependence on z is actually more direct, but I'll have to do this at least for wx and wy. Okay, so this is the basic idea. So as I pointed out earlier, the backpropagation algorithm has two components. The first is invocation of chain rule. Is the idea to help differentiate output with respect to input in terms of hidden layer activations. Okay. GQ is like a hidden layer activation here. By the way, I keep referring to sections of the textbook. So I think most of my slides will have these section numbers where you can read it up further if you want. So what backpropagation will do is randomly initialize weights. Before you do backpropagation, you'll have to do a forward propagation. You'll have to get the f in terms of the inputs. Obviously, that's when you can differentiate. And then you'll compute the partial derivative of the error with respect to each of the intermediate w's, weights. and then use gradient descent to try and minimize the non-convex EW. This non-convex EW is our error function, and we will soon see that it's nothing but the commonly used error function generalizing the cross entropy of logistic regression, the cross entropy loss function for neural network. So you will compute the gradient descent in order to try and minimize this non-convex EW, and you will keep doing this while verifying that EW is indeed reduced. Now because you are dealing with this very unwieldy space, search space, non-convex search space, you may land up somewhere here, right? So what you do is, to counter that, you may also resort to some random perturbation of weights W. Okay, and why are we doing this? This we are doing to help address non-convexity. And this is the image you can keep in mind. Non-convexity means you will have this, I am not necessarily a teddy bear all the time, but you could have these different regions. One region may not connect to the other. So this is a high level idea, and when I say now compute the partial derivatives, that is where you will use chain rule. Okay, so chain rule is basically coming here. So the question was, why do we talk about random perturbation? So let us say I am getting stuck here, right? Either I will randomly perturb the W or again restart with some different initialization, so that with the hope that one of my perturbation gets me to this area. So this had minus 100, this was stuck in minus 10. Okay, so idea is to help escape local minima. Is that clear? Now there are multiple ways you can do it. One is you can start all over again with a different initialization. You have done perceptron, right? Logistic regression. Start with a different initialization. That might not have affected logistic regression much, but perceptron probably is. That is the rate of convergence. But here the solution itself might change. And other possibility is, don't restart, start wherever you are, just kind of try and randomly add some noise to the weights and see how you progress, with the hope that you are able to move out of this. Let us say even if I am able to jump here, right, I am here, and from here I am able to jump here somehow with my perturbation, I still have the hope of getting to some different minimum. Yeah, that's a good question. So you may use validation data here. So question was, when do you know that you should perturb EW? So you may find that your training data, okay, this guy hasn't learned anything so far anyways, but you may sometimes find that the training loss is decreasing, but some test loss or validation loss is increasing. Okay, so here, right? So you will find that the test loss is confused, 2.59, 58, 59, 59, and test loss is confused, training loss 2.32, but how, right? So now this may be a recipe, since the test loss is a bit confused, wavering, you may say, okay, let me randomly perturb and see. Unfortunately, I can't do that here in this interface, but you could, if you code it up yourself. Is that clear? Okay. So now one may ask, okay, I do chain rule, but I mentioned memoization. Why memoization? So chain rule is one part of backpropagation. right. So chain rule is saying that loss is here, output with respect to the output I can directly compute the partial derivative, right. So if I wanted to compute, so let us say with respect to this layer, this is directly computable. But if I need the loss derivative with respect to any of the intermediate layers, I need chain rule. Right, you need the chain rule. So that's fine, but is there a possibility that I am inefficient here? All these are the GQs, right? These activations are what we were referring as GQs, and this here output layer you had the GF. Now is it possible that the same partial derivative gets invoked multiple times in the hidden layers? Yes. So is it possible that, let us say f is a function uses q q1 xy comma q2 xy. So q is in terms of q1 and q2, r is in terms of r1 and r2. These are so f has two arguments, q and r. In turn q has two arguments, q1 and q2. R has two arguments, r1 and r2. That won't be as, let me actually take the simpler case. All of these are interesting, but let me take the case where q1 is part of r, q1 and q2 are part of r. This, let's take this example. So q1 and q2 are invoked in q as well as r, and that's what will happen. One of these hidden layers is used here, right? So it's very much possible that, say, this is q1, this is q2, q1 and q2 both go to q, and q1 and q2 also go to r. This makes sense? Is this possible? I mean, this is how networks are designed. So now if I have to look at the partial derivative of f with respect to x, x is not the input, x is some intermediate weight. Okay, so if you want, call these as w's. It's too many, I have to rewrite all over again. So if I had partial derivative of f with respect to, let me do that anyways, I'll make that correction. I'll use w instead of x and y, just so that q1 w1 w2 q2 q1 w. So I want partial derivative of f with respect to w1, and I know that these dependencies are at some point of time through q1s and q2s, and now I have to compute, and this will be a function, this will involve partial derivative of f with respect to q, and then q in terms of q1, and then q1 in terms of w1 plus So I will only take some components, there are many components. Partial derivative of f with respect to r with respect to q1, and then q1 with respect to w1 and so on. Okay. So of all these, let me just draw your attention to partial derivative of q1 with respect to w1, which occurs in two terms, right? Now when you compute the partial derivative once, do you have to compute it again? Just store it, and all you have to do is be smart about saving these computations so that you can quickly retrieve them. Okay, that's where memoization comes. So the second part is memoization. So what we are pointing out is you can memoization of all these q1 w1, q1 w2, q2 w1, q2 w2 and so on, can speed up computation. Now I showed you only at the level of these basic units. I was trying to show a more complex case, but it just take up all the space. Now think of not just these basic computations, but imagine that functions, you had functions of functions, and some of these were recurring, right? You know that the intermediate layers, they are themselves complex computations. They are not just, they are not based on input alone. So you could have complete logical units being repeated, which means it's possible that complete chain rule products are being repeated. It's not just these simple components. There could be products of these which are repeated. Why do you need to multiply them all over again? Okay, so memoization is all the way through. It's a huge thing. So memoize the partial derivatives products and sums of products. So it's not just again products, you can do memoization of sums of products as well. This is the second part. Is this clear? Okay, so here's the notation for backpropagation. So now we are talking about this point 3. And the notation is as follows. So for the time being, we are only dealing with hidden layers, okay? Hidden layers and output layers. Input is just the first hidden layer, think of it that way. So this is the L minus 1th layer. This is the Lth layer, and this is the capital L. This is the final layer, final or output layer. Now how are these layers connected? They are connected through sums of weighted activation units from the previous layer. Okay, so an activation unit here, let me show an arbitrary activation unit here, and let me show it in bigger size. This is also another arbitrary activation unit on the Lth layer. Okay, this is the Lth layer. L minus 1th layer. So this activation unit is sigma superscript L minus 1 J. Oh, I call it I, sigma I. And this is sigma superscript L subscript J. The weight connecting sigma I from L minus 1 to sigma J in the Lth layer is Wijl. Is this visible to everyone? I mean, either the board or what I have written on the blackboard, either the slide or the blackboard. Is clear? I'll enlarge this. So, this is Wijl and this is sigma JL. And the sigma JL is being fed not just from this I from L minus 1, it is being fed from many such I's from the L minus 1th layer, and each of them is being weighted by Wijl. So I will call this sum, the sum coming into, let me start this. So sigma JL is the activation function applied on sum coming into the jth node, from the previous layer. This is sum JL, and in turn the sum coming into the jth neuron in the Lth layer is a weighted sum of the activation units from the previous layer, Wijl into sigma I L minus 1 for all values I in the previous layer. Okay, I will write this again on the board. This sum JL, as the name says, is a summation over I's, summation over all the I's here of sigma I L minus 1 into Wijl. Now if you want to be more specific, what this I ranges from I equals 1 to the number of nodes in the previous layer, which I call SL minus 1. So this I say has magnitude as SL minus 1 nodes, the Lth layer, L minus 1th layer, the Lth layer as SL nodes, and the last layer as capital SL nodes. But as far as writing on the board is concerned, I'll try and avoid using this SL. S is just the range. Otherwise, summation over I will just mean everything in that layer. And now, whose gradient are you going to compute? I said it's a cross entropy, but it's a cross entropy and I slightly improvised for the multi-layer neural network. So it has two components. It's something I'm not going to write on the board because you're all familiar with cross entropy. Now it's a cross entropy but regularized. Okay, so the first part of the cross entropy is the regular cross entropy computed with respect to the output nodes. So this part is our routine cross entropy computed with respect to the output layer. Okay, so therefore output, when I say output layer, I mean output layer activations, which are nothing but sigma superscript L subscript K. These are the activations. Okay, so these activations are sigma K L. This is where you can compute the error, because as I said, the error cannot be measured on something that is unseen, the hidden layers. You only observe the input and the output layer. But the regularization, that regularization you can now have explicitly on every weight and every layer, right? So this is the regularization. So every weight in every layer, and when I say every layer I mean L equals 1 to capital L, is explicitly regularized. Okay, so in some sense for the regularization component, would you need chain rule at all? Do you need chain rule for the regularizer? No. So chain rule is actually for the first component. So chain rule and also memoization are because of the first component. So even if you remember the function f, which was a function of g, right, of q, there I showed that the dependence on z was more direct, the dependence of f on z was direct. That's exactly the case here. W else the regularization component, there's a direct dependence, no indirect dependence. But after this point we will not really bother too much about this form all the time. I mean, we will use this form at some point of time. Okay, now we will look at the backpropagation flow graph in details, and there is an interesting illustration. Let us actually see this. This is for the convolutional neural network, which I will introduce maybe next class. But let me just show you what is exactly happening. So this is the input. The input, what you are getting here is a digit. Okay. Now I am showing some activations, but you don't have to use convolution right now. Let's just imagine that these were some hidden layers. Input goes into some hidden layers. What you see here are the activations and activation gradients, or the gradients of the activation units. There are some more layers, different activation functions are used, and so on. And let's look at what the final layer looks like. This is the final layer is from where you backpropagate. So in the final layer, the activations tell you which digit it actually is, right? So I mean, if the input was 4 and this looks like 1, so output will be 1. If this is 2, output will be 2, and if this is 7, output will be 7. So output will always be correct. Output in the sense the ground truth output on which you measure cross entropy. Okay, so the activations are exactly 10 in number. There are 10 activations in the output layer. Only one of them gets activated. Only one of them gets rewarded, right? Only one of them should be activated. So you can see the actual activation and the loss is computed if based on whether activation was peaked at the right place or not, whether the right digit or not. Now that will reflect. So the backpropagation starts from the bottom, starts from the last layer. So from there now you compute the you had known the activations, you will compute the gradient for those activations, right? For this layer it's just one step. But now as you go inside, you need to compute the activation gradients for the previous layer using chain rule and memoization based on what came from the next layer, and then you go further up, right? And then you go further up. Okay, now all these become very important, and then you can also see how the weights change. And now the visualization is also here for a purpose, for an intent. The intention is that the activations actually start making some sense. So if it's a 7, then some activations are meant to take care of the horizontal stroke, some activations are meant for the vertical stroke, right? So that putting together horizontal and vertical stroke gives you 7. But if there is only a curvature all through, then some other activation unit should be on. So all these hidden layers are capturing different aspects of your 0 or 1 or 2 or 3 or whatever, your vocabulary of digits. As MNIST, since it will be a data set that you will have in your lab, I am just illustrating it. The backpropagation goes backwards all the way to the top. So to get to these activation gradients, the first layer you have to kind of backpropagate all the way up because of chain rule, because of the fact that the dependence is indirect, not direct. Any question? If it's clear, then we'll go on to the details. And this, unlike this problem, right, where we are dealing with a binary classification, now we are dealing with multi-class. You have 10 classes, and because you have multi-class, now you are doing this 10 activation units, and you are using softmax. I talked about softmax in the last class, generalization of the sigmoid to multiple classes. Okay, so this is binary classification. Binary classification looks like this, just one, and for multiple classes, MNIST, the number of classes is 10, classes are mutually exclusive, hence the more general softmax is used at the output instead of sigmoid. Okay, this is exactly what I showed you just now. This was the binary case, the earlier one. Here also you could visualize the flow, but it makes more sense in this setting. The activations are very graphical. So we use a more general softmax. Okay. Okay, so this is the case of multiple classes, multiple softmaxes here. So each of them will be activated to a 0 and 1. Okay, so now we will get to the details. Okay, so remember that we have an L2 regularized cross entropy loss function, and the activation unit we have used is the sigmoid. These are the only two specific, these are the specific choices we have made. But does backpropagation depend on these specific choices? No. I mean, the detailed steps will change, but the spirit of backpropagation, memoization and chain rule are not because of this loss function. Any loss function will have the same. You will need the same two tools. Okay. Okay, let's write down the steps for this backpropagation. So it starts with this. I want the partial derivative of error with respect to any Wij. How do I unfold this? My Wij is always visible only through the sigma at the nth layer. So that this is where I'll begin with. Partial derivative of E with respect to sigma j at the nth layer. These are dotted lines. So error is computed here, and now you are trying to backpropagate the error, the gradient. Now this sigma jl is a direct function of Wijl, and it's a direct function, but it's direct, but it involves other sigma j's as well. So what I'm going to do is I'll write it in terms of sum. Sigma jl is a function of the Wjl through the sum. The sum of all the weighted activations from the previous layer. And this sum now I can express in terms of the Wij's. Okay, so please give me all these terms, just give me these 3 terms. Please can go on. So tell me what this is, what this is, what this is, and then help me identify where memoization will surface. Yeah, I'm showing the same equations in this flow graph. Sigma JL. I made a small mistake here. I'm so sorry, I have not made a mistake. This part you will get some hint from the slide here. So I said that E depends on Wijl only through sigma JL, right? Because Wijl doesn't feed to any of the other sigmas. But the partial derivative of E with respect to sigma JL you have to compute a little carefully. Because sigma JL itself depends on all the previous guys. Okay, so that might help you. So I conveniently dropped all the other sigma JLs here when I took the derivative with respect to Wijl because of the architecture. But then this, if I have to further compute this, I'll have to keep in mind that sigma JL itself has dependence on all the previous sigmas. And that's exactly where backpropagation comes in. So keep this in mind. The slide plus what I have written on the board. Slide is a hint. What I have written on the board is a question. I would appreciate that everyone writes. So there's a question that why is this L plus 1? Should it not be L minus 1? Okay, so interesting question. I said that the sigma JL depends on the activations on the previous layer. But the derivative of E with respect to this guy, the sigma JL, will depend on how sigma JL fared on the following layers, right? So just as I said, this guy depends on all the previous layers. The next layer, activation in the next layer depends on all these activations. So that's what you have to think. Now when you talk of dependence of the sigma JL on its previous layers, extend that and say that the sigma JL plus 1, all the activations in the next layer actually depend on activations in this layer. So the only way I can compute the activation with respect to sigma JL is with respect to where it fed into, because error was computed based on where it was fed into, not where it is getting its inputs from. Error is always computed here. So if I have to be practical, I'll have to look at how sigma JL influenced. So let me not use sigma this L plus L, let me use L plus 1. Let's just imagine that this is L plus 1. So I have to account for how sigma JL influenced all these nodes in the next layer. So this was good, I expected such a question. Please ask questions. That's how the algorithm will unfold itself. If you didn't understand the question or the answer, please let me know. That's a very important question. What would happen in the last layer? So in the last layer, this part, partial derivative of E with respect to the sigma activation would be direct, exactly as in logistic regression, right? So it will be the answer to your safe quiz. I mean, if you took the quiz last week, so all of you are familiar with that. So that will be very. This first part becomes very simple for the last layer. Or L is less than capital L, you can use what I have on the board. Now this L feeds into L plus 1. And let's say these were indices P here, P equals whatever. I'm not going to write down all the detailed summations, the ranges of the summations. So partial derivative of E with respect to this activation will depend on partial derivative of E with respect to the activations in this layer, the following layer into which it feeds, multiplied by the weight. Right, all the other weights are constant. I mean constant in the sense you are only differentiating with respect to one weight at a time, right. So it's exactly Wij. So all the weights connecting the Wj P L plus 1, right, these are fixed. I mean in the sense I am not differentiating with respect to them. They are not functions directly, they are different parameters. So this is what I have from the board. The first component. Now that itself is a summation, as you can see. But that summation is what I will be able to unfold using memoization. So the question was, in the last layer it becomes simple. Think of the second last layer. Now since the last layer we have all the computations, I will reuse in the second last layer. So this is basically coming from the previous, the following layers, the computations that have been already done. This have to be stored. These are the summations that have to be stored. It's not just individual values. Okay, so you have similar summations all over here. This is backpropagation in action. And now you are letting that go down here, right. So I have deliberately kept here, I have deliberately kept the regularization kind of different because there is no backpropagation in the regularization, right. I mean you can consider that E contains regularizer term, or you may just consider E to be the cross entropy term and regularizer is separate. So here in slides this has been kept separate, okay, and because it has been kept separate, the partial derivative of that has been reflected here separately. But the other term is exactly what I have here. So I'm going to ignore the regularizing term. It's just lambda by, I mean it's just going to be that same thing, lambda by m times Wij. Okay. Now tell me the form of the others. So this is fine. What about the form of the first component? Sigma JL divided by sum. This will be exactly the sigmoid form. Sigma is sigmoid. What is that derivative? 1 upon? Yes? What is that? Oh, sorry? Sorry? F of x into 1 minus x. So it will be? Or I can write it in terms of sigma itself. Sigma JL into 1 minus sigma JL. This is because of sigmoid. So right, this is the sum JL. Now, I mean you can substitute for sigma JL here again in terms of this form, but I'm like making it compact. You have done this so many times. This is basically from recall logistic derivation. no point writing everything all over again. What about the third component? This should be the simplest of the lot. What is the third component? Sorry? The third component comes from this. Make sure everyone has the safe on, working. Otherwise take your, I am just completing this obvious thing. Yeah, what is this? Sigma I L minus 1, that is it. It's a very simple term. Okay, so now you can do this for a single example, which is what stochastic is about, right? Instead of doing this for all examples, we complete it for single example, and these are the three equations, exactly what I have written on the board. And on the first term you use memoization. Okay, but we will continue on this in the next class. I mean, all the equations are there. Next class I will assume that you understood the derivation.